So the topic for today is we're going to complete the proof of the Cook-Levin theorem, and then we will see more examples of NP-completeness. So just to recall, we want to prove that SAT is NP-complete, and I defined what SAT is in the last lecture. The way we will go about doing that is, so we need to show that for any language in NP, M, this language script M, can be reduced to SAT. And so this is the process. So in some sense, what I am describing is really the algorithm. And but it's gonna be a somewhat long-winded description of the algorithm. So it's first useful to think of a thought experiment. So consider script M. That means there is a standard non-deterministic Turing machine M that decides script M, and it runs in at most n to the c steps for all computational paths. So what we're going to do is we're going to invoke this method called the Tableau method. Now, as we discussed, one can consider the running of this machine M on an input X. If you take any snapshot in time, you can represent that snapshot by what's called a configuration string. Okay, the configuration string records the tape contents and records the position of the head, and it records the state basically by a symbol. So this is a string that represents the situation or the state, the entire state of the machine M. Sorry, did someone have a question?
No, I think someone had just joined in.
Okay. And the length of this string is at most n to the c, and that's because it's at most the total tape contents. Now, the notion of a configuration string is going to be very important for us. We're going to revisit this definition over and over again in subsequent proofs. So, a tableau you can think of as in n to the c, which is the number of time steps, cross O of n to the c, which is essentially the tape length, which is n to the c plus 1. And maybe you encode it in some other language in binary, so it could be it's O of n to the c cross n to the c. Just think of drawing this matrix of symbols. Each row is a different configuration of a different time. So the first row or the 0th row is the input configuration. The first row is the configuration after step 1. The second row is the configuration after step 2, so on and so forth. So consider some running of the machine where the machine may make its non-deterministic choices and then it runs. We can define capital XTK to be a variable which is simply the symbol at the tkth position in the tableau. And think of this as sort of some character in the configuration string, so it's a variable in sigma union q. And if you want to think binary, you can, well, okay, let's not do binary because it's convenient to have q actually being the state, and this may not be binary. And so this tableau it represents the running of the machine. Okay, now at this point I haven't told you anything about the reduction. Now the key is the following. We can say that X is in M if and only if there exists a setting of the tableau, meaning that you can fill in the tableau such that the first configuration is the input, the last configuration is accepting, and each intermediate configuration follows from a previous configuration using a transition. If there is a setting of the tableau, then that's like a certificate that X is in the language, because that gives you the entire computational path. Moreover, if X is in the language, then there must be a computational path that accepts, which can be encoded in this form as a filling out of the tableau. Now, what we also discussed is if you are given in a filling of the tableau, checking it is really easy. It's just linear in the tableau size. So if you think about it, we're already doing something. This feels like this is exactly how NP works, right? So there is a certificate, and the certificate is easy to check or is efficient to check. So there is a polynomial size certificate that is efficient to check. Of course, this certificate was literally just the running of the computational path. So what we are now going to do is we are going to convert this entire statement 1 to 3. We're going to convert all of this into a Boolean formula. So we're going to write down a Boolean formula that is satisfiable if and only if these conditions hold. Are there any questions at this point? So it's really important that you understand this logic, because now I'm going to discuss how we actually construct the formula. Any questions? Okay. So I'm going to break up the formula. I'm now going to write 4 formulas, 4 Boolean formulas. The first Boolean formula is going to be called unique. Now we said, xtk is a variable that takes one value, but I want to encode this in binary. So I'm going to encode this as I shouldn't say as binary, as a Boolean formula. I'm going to encode the fact that the start has to be the input configuration. The end needs to be an accepting state. And the fact that move follows according to the transition rules. Okay, so now I'm going to describe how that is done. So I'll say constructing the Boolean formula. So I'm going to define a collection of variables. So I'll say for all t less than n to the c, for all k less than whatever it was, some o of n to the c, so it's some, let's just say n to the c, and technically this is o, so maybe there's some constant c prime over there. This is just some constant. And for every alpha in sigma union q, I'm going to define a Boolean variable x t k alpha, which is true if I want to set x t k equal to alpha otherwise. So this is a way of encoding, and this is, as someone said, it's like a one-hot encoding. So I am just encoding what the value is using like a bit vector, and the length of the bit vector is the size of sigma union q. And what I need is just one of those bits needs to be true, and that would encode what the actual value is. So let me just write down what unique would be. So unique would say an and over all t less than n to the c over all k less than c prime n to the c. First, we need to say for a fixed t and k, one of these has to be true. So we'll say for all alpha in sigma union q, x t k alpha. So this has to be true. And at most one can be true. At most one can be true. So again, there are multiple ways in which I can encode this, and let me just give you one of them. I'll just say for all alpha beta in sigma union q, alpha not equal to beta, and I can say that x t k alpha not, I'm sorry, I think yeah, okay, x t k beta and I may have used this notation in the past, and it's the same thing as doing negating in this way, and I might negate one way or the other depending on how I want to scrunch up the formula. So this part of the formula says one xtk must take some symbol value. Xtk cannot take two different symbol values, because if two different things were true, then this part would become false, and it would make the entire thing false. So this is an encoding of unique. And note that the size of the encoding is polynomial in n. Right? The length of this entire length. So the size of the formula is, it's basically like n is O of n to the 2c. So this encodes unique. Does this make sense? Any questions? Okay. Now I realized I've overloaded my symbols here because I'm using x for the Boolean variable. I also used x for the original input. So I'm going to apologize. I'm just going to change this to w. I'm going to set the input to be w, and this is going to be more convenient for me because I define this as x. Okay, so this is unique. This is saying that each symbol takes one unique value. Now let me define what start is. A start is actually quite easy, and I'm just going to assume that the tape content is just going to be the input. So I could say I could basically say x 0 0 q0. Right? This is saying that the initial so what should the initial configuration be? The initial configuration written as a string should be q0 and then w1 w2 up to wn. Right? And then everything else is just going to be a blank. That's what the initial configuration is. So I can just encode this by saying this, and x, remember in the Tableau this is going to be the 0th row. So I'll say 0 1 w1 and x 0 2 w2, so on and so forth until x 0 n wn, and then it'll be x 0 n plus 1 and blank, and so on and so forth. So this gives me the encoding of the fact that the starting configuration has to correspond to the input. The ending configuration, now what that is going to say is simply that x, and by the way, we can assume that if you reach the accepting state, then you simply nothing changes, the configuration stays the same. So we'll say x n to the k 0 q accepting, or x n to the k 1 q accepting, or x n to the k 2 q accepting, so on and so forth. This is just saying that one of the in the final Tableau, one of these states one of the symbols has to be the accepting symbol. So are there any questions about this? Is this clear? Any questions? Okay, so hopefully that is clear. I just want to move this over here. Okay. Now the interesting part is where we do move. So for move, it is going to be convenient for me to introduce another auxiliary variable. So let's just say the transition function. Remember that the transition function is going to take sigma or q cross sigma to 2 to the q cross sigma cross left or right. And I'm just going to imagine that I could write out the transition basically as a table. Right? So I could have a table which basically says what is q and what is sigma. That's what it starts off with, and then it goes to q sigma, and then left or right. So I could just number these rules. 1, 2. This is going to be some absolute constant. I'm just going to call that constant d. I'm just numbering the rules of the transition table y1 to d. And now let me just introduce a variable. And again, this is just for convenience. This is just to show you that this is what, this is what is going to happen. So I could say y t of I, okay, where t is less than n to the c, that's the time, and I is going to be something from 1 to d. This is a Boolean variable that is 1 if the ith rule is used in the tth transition, and it's else 0. So now what we can do is we can ensure, using unique formula, ensure that for all t there exists a unique I such that y ti is equal to 1. Right? I could just repeat whatever ideas I did over here. Basically write the same thing, except instead of k here I have an I. Or actually not even that. For over here I just put an I. Everything else is like I remove the k. Right? So for all time steps there has to be some transition rule that is chosen. Then furthermore I can say, I can go through the transition table and I can figure out what rule needs to be chosen at every step. So I could say something like, well, let me encode it as follows. So what is move really saying? Move says that x t plus 1 k is a function of x t k minus 1 x t k and x t k plus 1. So what this is saying is, if you look at the Tableau and you look at the sort of 6 by 6 window, you say, look at this symbol here. What is this symbol going to be in the Tableau? It only depends on one of these three symbols. And this is key. This is actually the key to the encoding. Computation is a local phenomenon. So what it says is, what could happen here? So if there is no head, if the head is not in any of these, then this xt plus 1k is the same as xtk. So I'm just going to write this out, and then you'll see that it's possible to encode this using these. So what we can say is, for all t, again less than n to the c, k less than c prime n to the c,
I'll take a guess as to what's coming next.
I'm sorry?
Or how this is. Can I take a guess as to how?
Sure. So let me just write this out, and then you go ahead. So I'm just going to write this out. So I'll say that if xt k plus 1 is not a state symbol, and xtk is not a state symbol, and xt k plus 1 is not a state symbol, then xt k is equal to xt plus 1 k, right? And then you would encode all of this using the little x's as before. So you can encode this just by taking the and of x little x t k minus 1 with all the state symbols, so on and so forth. So this ensures that if the head is not there, then nothing changes. Now go ahead and tell me what you think will happen next.
Or rather, what I was imagining for this particular part is that the number of states of those three parts, or those three cells, or like the combined state of them is, or like the combined number of states that you can have them in is finite. And if we're considering all possible states of them in a bit vector sort of way, then you can kind of create a truth table of what is allowed for the next, or for the cell that's down one step.
Exactly. And indeed, what you can do is, using the YTIs, you can actually make it deterministic. Because the YTIs will tell you which rule is being chosen. So then at that point, you include the YTI in your formula as well, if that makes sense. And then everything just becomes completely deterministic.
But yeah, I was basically imagining that given a truth table that says what's allowed, you can create a Boolean formula from that truth table, like using disjunctive normal form.
Exactly. So yeah, I mean, again, there are multiple ways of doing this, and I think anywhere works. And essentially, you just have to encode all of these statements. What's important here, and as was just said, is that in effect, it's only a truth table of what happens in a 6x6. I'm sorry, not a 6x6, a 3x2 portion of the tableau. Right, so one has this, which says that this encodes the fact that if the head is not present here, then the symbol remains the same. And as was equivalently said, you could also create an entire truth table. Right, so you could create an entire truth table. You can say, if the ith rule is chosen in the tth step. So let's build a truth table, and the truth table is simply x t k minus 1. Okay, so let me write these as x t k minus 1 alpha, x t k beta, and x t k plus 1 gamma. So we're looking at alpha, beta, gamma, which are basically in the configuration string. So these determine x, or they basically determine, well, I should say these. I'm sorry, this is a bit of a mess. Okay, so I basically wrote, I'm just rewriting this, that this is a function of these three, I should say, and y ti. This is saying that if you specify which rule you're using, then using these three, you can write this as a function, and then you can write down the entire truth table here. So what is this truth table going to look like? We can say, okay, so let's look at x t k minus 1 alpha, x t k beta, and x t k plus 1 gamma. So if all of these are true, so we can say if this and this and this is true, then x t k will be delta. And this I can of course encode through my binary as just saying that x t k delta is true. Right, so if these are true, and what is delta given alpha, beta, gamma? That depends on what the transition table tells you. Indeed, if none of these were a head symbol, then delta is equal to beta. If one of these is a head symbol, then it depends on what the transition is doing. So if you put all these rules together, so you will say, So you kind of do an AND over all possible values of t, k, alpha, beta, gamma. So you AND everything together, and then you can take, finally, you can take unique and start and end and move. And move is a pretty complicated formula, but you take this entire formula and you refer to this formula. This formula I'm going to refer to as phi sub w, because it depends on the input. So it's phi sub w of x, and x maybe, and y as well, but x, x, y. Then this is true if and only if w is in the language. So this formula is true if and only if w is in M. So you can see that it's a bit of a tedious encoding, but you should see that it's doable. So are there any questions about this? Does this make sense? Like how one would construct this embedding? How would one construct this encoding? I'm sorry, not embedding, but encoding. So I'm just going to sort of poll you. So, A is, I understand this. B is, I need more explanation. And so please ask me more questions to explain what is going on here.
Could you go over, maybe whenever you will, why this is a polynomial algorithm?
Why this is in polynomial time? Sure, I'll explain this. Yes, okay. That's a good question. Okay, so I think, it's worth, let me just describe this again, and maybe this will help. So remember, we're encoding the Tableau. We're saying the Tableau has to satisfy these rules. I'm going to encode all of this in a formula, and I'm going to argue that the construction of the formula can be done in polynomial time. The construction of the formula can be done in polynomial time. Okay, so why is that? So you look at this formula here. You can imagine writing an algorithm that would simply output this formula. This formula is actually independent of W. Right? I've actually written down the formula, so you could write out the formula explicitly in whatever ASCII encoding you want. Right? So you just simply write out this formula in ASCII. But you can't use the summation symbols, right? So you actually write down the formula explicitly in ASCII. This is a compressed representation. You would give it the full representation. You would just write it out. Let me come back to start in a bit. We'll come back to start. And you can explicitly write out. This also doesn't depend on the input. Move is a much more complicated formula, but there are only polynomially many variables, and each formula that I'm going to describe here only has polynomial length, right? So you have polynomially many such variables. The unique encoding for each of them is only of polynomial size. Actually, indeed, for this, it's just going to be constant size. For each t, you have a constant size formula that says one of these must be true. And finally, you have this formula. Say, if the ith rule is chosen in the tth step, then this happens. So this is just saying that if this and this and this and yt of I, then this, where basically the delta depends on alpha, beta, gamma, and I. Saying that if the ith rule of the transition table is chosen, and this is alpha, beta, and gamma, then this must be the next symbol. This is just a constant sized formula. You can imagine an algorithm that writes down this constant size formula, and this constant size formula is written down for all t and all k and all beta. So I should say that this would be for this is like an AND over all values of t, all values of k, all values of alpha, beta, gamma, and I. Right? So it's an AND of all of these. The AND of all of these is move. So all of this, you can imagine just an algorithm that simply writes all of this down explicitly. The only thing that depends on the input is the starting configuration, but this is again something that can be written down. In this case, it's just linear time. You simply look up what the first symbol of the input is and you write down the encoding of that variable. Does this make sense? Questions?
The move part, since we were iterating over like 5 or 6 variables, it stays polynomial time in total?
We're iterating over the. Okay, so maybe what? So which one is the one that you think will not be polynomial? Which is the one that you have confusion over?
At the bottom of when you made that big and symbol at the bottom.
This one.
Yeah, that one.
Yes. Okay, so t is less than n to the c. K is O of n to the c. Alpha, beta, gamma, and I are all O of 1. So it's just the product of all of these. Right? So the total number of clauses here is something like O of n to the 2c.
Okay, I forgot that alpha, beta, gamma would be constant.
All of these are constant, right? Because these are just in the alphabet. I mean, even if they were polynomial, it would still overall be a polynomial. But, right? So essentially, let me sort of write down. So given W, or I should say there is a O of n to the 2c time algorithm. And sorry for writing small. Let me just increase the size. I'll say there is an O of n to the, I'm just going to give myself some extra slack and say O of n to the 3c algorithm. I'm only saying 3c because it's actually 2c, but I'm just tacking on an extra n to the c in case, because you have to write things down, and each symbol takes some time, and there's some encoding, and there's a log n encoding for all of these things. So just absorbing all of that. That given W explicitly writes down phi of W of x. Right? Phi W of x is simply a sentence. It's just a sentence. It's a Boolean formula. So you can imagine that it is actually just writing down the exact encoding of this formula. And the formula over here, as we discussed, is this unique and start and end and move, where move is an and of many things, unique is an and of many things, start is an and of many things, end is an or of many things. But all of this is just written down explicitly using a procedure, and that procedure is sort of what we described. We described how to do this, so you can see that there's an algorithm that writes it down. That algorithm doesn't do anything clever beyond just like writing down all the things we said. Explicitly writes down phi W of c, and remember that phi W of x is satisfiable if and only if the Tableau conditions can be satisfied if and only if x is in the language. Therefore, this algorithm is a reduction. It's a reduction. It shows you that M can be efficiently reduced to SAT. And that would be the end of the proof. Okay, so this proves the Cook-Levin theorem. It proves that SAT is NP-complete. It actually proves it's, yeah. So why don't we pause here for a few minutes, and I'll answer whatever questions you have, and then we can proceed with the next part. Now that actually we've proven that SAT is NP-complete. Let's look at specific subversions of SAT that also happen to be NP-complete. So we're going to look at normal forms of Boolean formulas. So recall that, if so phi1, phi2 are formulas, the conjunction is just the and the disjunction is or, right? Conjunction is and, disjunction is nor. So CNF, called conjunctive normal form, basically means that it's a conjunction of disjuncts. So this just means if phi is and of ors. So these are the clauses. So for example, conjunctive normal form, if phi is in conjunctive normal form, you would say something like x1 or x3 not and x5 or x2 or x10 and so on and so forth. Similarly, you have something called DNF, which is disjunctive normal form, where now you would flip it. It's an or of ands. So phi would be x1 and x5 or x10 and x5 and x3, so on and so forth. So we can always assume that negations are at the literals by De Morgan's law. Right, so you can verify that. By the way, in whenever you have a formula written in CNF or DNF, the negations are always at the literals. But for any formula, you can get the negations to be at the literals just by pushing it down through De Morgan's law. It's convenient in general. So let's look at what is the representation of a formula. And you've probably seen this. A formula phi can be represented as a tree with internal nodes labeled and or and leaves labeled with literals. Remember, the literals are the variables x1 to xn and the negations of variables. Right, so you can always, what does De Morgan's law say? De Morgan's law just says that if you have and things are negated here, then you can convert to an or, and you can negate these, and then you can push these down, right? So this is what De Morgan's law says. And I'll say two formulas, phi C are equivalent if they have the same value for all settings of variables, of two over the same variables. And of course, any phi can be converted to an equivalent C in CNF or DNF. Right? So you can convert anything to conjunctive normal form or disjunctive normal form using De Morgan's law and the distributive property. So any phi can be converted to an equivalent phi in DNF. Okay, so now let me ask you a simple question. So let language DNF sat be all phi. Phi is satisfiable and phi is a DNF. So here's my okay, so my question is somewhat more complicated. So let me first state a theorem that we're going to prove. I'm going to prove that CNF sat, which is the equivalent version where phi is a CNF, is NP-complete. Previously, we just showed sat is NP-complete. But now this is saying even if you do CNF sat, it's NP-complete. My question now, which you have to think about a bit, is that TNF sat is NP-complete, or DNF sat is probably not NP-complete. The reason I say probably not is because it could be that P is equal to NP and then everything is complete. Like so. This is the poll. So think about it. So I'm going to prove this. I have not proven that CNF sat is NP-complete. I will prove it to you. But assume I told you CNF sat is NP-complete. What about DNF sat? Is DNF sat also NP-complete? Or do you think that DNF sat is not going to be NP-complete? Remember, and we said that any phi can be converted to an equivalent C in CNF or DNF. So you can switch between CNF and DNF. So I'm going to launch this poll. Think about what DNFs are and think about what CNFs are. Okay, so the answer is it's probably not NP-complete. Why? DNF sat is actually in P.
Well, it's an or of ands, so you can just take one of the clauses and try to and just literally satisfy it.
Right, so you basically just go over each clause and you say, can you satisfy it or not? It's an or of ands, right? So in DNF, it looks like this. So you could just go and check, oh wait, I can set x1 to 1 and x5 to 1, and that's it. I don't even have to look at the other clauses. Here, it becomes complicated because if I set x1 to true, it satisfies this clause, but now I need to worry about the other clauses because it's an and. It's an and of or, so you have to satisfy all these clauses. In DNF, you only have to satisfy one clause. You only have to satisfy one clause, so you can just go and check, oh, could I satisfy this clause? Yes, I can. Then that's it. Now, why would you not be able to satisfy a clause? Well, you may have clauses. Suppose your clause was x8 or x8 negation. Well, then you cannot satisfy such a clause. But then that's easy to determine. You can just go to each clause, which is just an AND of a bunch of things, and check, and you just set all of those to be true. So any question, is it clear why DNF SAT isn't P? Okay, but now now here's the more challenging question. I'm telling you CNF SAT is NP complete. We just discussed that SAT is NP complete. We saw the entire proof. SAT is NP complete, but any phi can be converted to an equivalent DNF, and DNF SAT is in P. So why have I not proven that P is equal to NP? Because I said SAT is NP complete.
Well, we don't know that there's an easy way to convert from a, well, or rather, I guess, DNF SAT, it's only one layer, whereas the Boolean formula we have can be multiple layers of ands and ors and such.
Sure. But, I mean, the conversion is fairly straightforward. The conversion is straightforward, right? You just use De Morgan's law. So, I mean, anything can be represented as a tree. So you use De Morgan's law and then you use distributive law. Does my question make sense? So please ask me. Okay, I'm going to poll you and say, does my question make sense? I'm seemingly providing a proof that P is equal to NP, which obviously has to be wrong. Do you understand my question? Not do you see the answer. Do you understand what the question? Do you understand the paradox I'm trying to say? So let me say it again. I'm going to poll you and ask you, say yes or no, that I understand or not. SAT is NP complete. Okay? I'm now going to give you a polynomial time algorithm for SAT. Any phi can be converted to an equivalent DNF. So I'm going to do the conversion to DNF. DNF SAT is in P. So again, my question is simply, do you understand my question? A is yes, I understand. B is it's not clear. Okay, so if for anyone who's not clear on this, please ask me some questions. Like ask me, okay, so which part is not clear? For those of you who, some of you said that this is not clear, let me sort of say this again. So any formula can be converted to an equivalent formula that's in disjunctive normal form. And remember, disjunctive normal form is this. It's an or of ands. So it's something or another clause or another clause, where these clauses have ands in them. You can convert any one to the other by the distributive property, right? Just by distribution. So the question is, I can convert any formula into disjunctive normal form. We discussed that disjunctive normal form is in P. DNF SAT. Determine if a DNF is satisfiable is in P. So why have I not proven that SAT is in P? That's the question. Now tell me, what is the resolution, or where's the bug in this proof?
In the chat, someone had commented because the conversion to DNF is not necessarily in P.
Okay.
My comment would be, I guess, then that's the, well, you haven't told us, or well, actually no. Well, you're saying distribution.
I'm saying distribution.
In that case, it may make there be too many clauses, or like an exponential amount of them.
Exactly. The conversion is not efficient. The conversion is not efficient. C could be exponentially larger than phi. So I gave you a reduction, but it's not an efficient reduction. Right? So what I can show you this. But this is just your typical mapping reduction. This I have not been able to show you. I mean, we don't know. Maybe it's true. But this I didn't show. I just showed you that there is a reduction, and that reduction is actually pretty straightforward. You use the distributive law, but the distributive law could blow up the size of the CNF of the formula. And that's why the fact that CNF sat is NP-complete is non-trivial, because given any phi, I could convert to CNF, but maybe it's going to blow it up. Does this make sense? I mean, please ask me. Ask me questions if this is not clear. So I need to do something more. I need to do something more to prove that CNF sat is NP-complete. And this is where I'm going to show you some tricks which are going to be helpful in some of the homework questions. So I'll say given phi, which is just some formula, we construct a CNF C of polynomial size such that phi is satisfiable if and only if C is satisfiable. But they are not equivalent. Indeed, they're not even going to be over the same variable set. So these two formulas, phi and C, only share this property that if one is satisfiable, then the other is, if and only if. But they're not going to be equivalent. So we're going to actually build C bottom up or through recursion. So let me describe how this process is going to work. So let's say, suppose I want to be careful with my notation. Okay, so let me say C1 and C2 are CNFs. So then obviously C1 and C2 is a CNF. But C1 or C2 is not a CNF. So what I'm going to do is I'm going to give you an equivalent. I'm going to show you how to get the equivalent. So what we'll do is we'll say C1, because it's a CNF, is going to be something like F1 and F2 up to Fk, where these are clauses, right? And these are disjunctive clauses, right? Each of them is basically a bunch of, it's an ORs. C2 is saying that G1 and G2 up to G, let's say K prime. Now what does C1 or C2 say? It says, well, either all of these are true or all of these are true. And it's not all, it's like, not exclusive or, but just or. So these are true or these are true. So I'm going to create C prime just by adding a dummy variable. It's going to say F1 or Z and F2 or Z, so on and so forth up to Fk and Z, and G1 or not Z, G2 or not Z, and Gk prime or not Z. So I have Z, and then I have the negation of Z. Okay, so if C prime is satisfiable, then if C1 is satisfiable, then you satisfy C prime by z equal to 0 or false, which would make all of these automatically true, and C1's satisfying assignment. If C2 is satisfiable, then you satisfy C prime by setting z equal to true and z2's satisfying assignment. Okay? And now I'll prove the converse. I'm sorry, I messed up here. I meant something else. So I said if C1 or C2 is satisfiable. I'm sorry. If C1 or C2 is satisfiable, that implies that C prime is satisfiable. Now I need to show that if C prime is satisfiable, then C1 or C2 is satisfiable. And that you should see is easy, because if C prime is satisfiable, then Z is either set to 1 or it's set to 0. So if it is set to 0, then all of this must be satisfiable. If it's set to 1, then all of this must be satisfiable. Okay, I'm just going to write that out and then I'll explain it again. I'll say if C prime is satisfiable, then the satisfying assignment sets Z. So there exists a satisfying assignment and it sets Z if Z is set to 0 in the satisfying assignment. In the satisfying assignment, then C1 is satisfiable. If then C2 is satisfiable. Right, so this is just saying that C1 or C2 is sort of is satisfiable if and only if C prime is in SAT and C prime is a CNF. Right? C prime is clearly a CNF. So if you have...
Yeah, but...
Yeah? Questions? Does this make sense? So you can replace any OR you can replace any OR by an AND with this extra variable. So you have to introduce one extra variable. Okay? So this is of course just doing it for one OR gate. So what you can do in general is you would start by representing phi, which is your original formula, as a binary tree. and then recursively make each subtree into a CNF that is satisfiable if and only if the subtree is satisfiable. Right, so recursively make each subtree into a CNF that is satisfiable if and only if the subtree is satisfiable using the construction we just discussed. Because if you have this, well, then there's nothing to do. This is just a CNF. But if you have a CNF or a CNF, then you use construction, and what you end up with is a CNF. Now this is going to blow up the size of the formula. The formula is going to increase each time. So let's try to understand how much that increase is. So if the size of this was K1 and the size of this was K2, the size is basically, let's say the size is definitely an upper bound on the number of clauses. You can say the size is the number of symbols used to write things down. Then the construction adds one variable to each clause. It adds one variable to each clause. Right, so whatever number of clauses you have, you're going to add a variable to each of the clauses. And so, but the total number of clauses remains the same. So it's important that the clauses are not doubling each step, right? So the total number of clauses, if you have k clauses and k prime clauses, what you end up here is with k plus k prime clauses, except the size of each clause goes up. The size of each clause goes up. So let's just say that you have K1 and K2 clauses. The construction will also have K1 plus K2 clauses with K1 plus K2 additional literals. Right, so you're going to add K1 plus K2 literals to this. Okay, so is this clear? So the number of literals added is essentially the number of clauses that you have. So if you sort of go through the calculation, you'll see that I think the best way to describe this is to say it is to keep track of the extra clauses, the extra literals that are going to be added. Each OR gate adds a literal, right? Each OR gate adds like a new literal, and this literal is going to appear these many times, where it's the number of clauses below. So we can just bound this by saying that each OR gate adds a literal to at most O of n clauses, because that's how many clauses they're going to be, because that's just the size of the representation. And there are at most n OR gates, so the total size is O of the number of OR gates times n, which is O of n squared. So this is a polynomial time construction, right? And this gives the reduction from SAT to CNF SAT. So let me pause here and take any questions that you may have on this. Now, having talked about SAT, CNF SAT, let's now talk about KSAT. So KSAT is the language. Well, sometimes there's no dash over there. It's all C. So C is a satisfiable CNF where all clauses have exactly K literals. So this is KSAT. So in CNF SAT, there's no bound on the number of literals in each clause. So one way to think of it is CNF SAT says, here's the tree representation. It's an AND of ORs. And this could have any size, any degree. KSAT is much more structured. It says that this has to be exactly K. The degree of these nodes is exactly K. This is CNF, and this would be a KCNF. And KSAT is the language of satisfiable KCNFs. And so now we have the theorem that you've probably most commonly seen, is that 3SAT is NP-complete. So I hope you understand what we're doing. We started from any Turing machine. We converted that to SAT. From SAT, we go to CNF SAT. And from CNF SAT, we're going to go to 3SAT. So now the proof, and again it uses this sort of dummy variable construction. So 3SAT is obviously an NP, simply because 3SAT, it's a sublanguage, it's a subset of SAT. It's a sublanguage of SAT, and so it's very easy to determine whether it's in the you can just check if it's a 3SAT instance, and if it is, you get the satisfying assignment as a certificate. So we show that CNF SAT can be reduced efficiently to 3SAT. So all we need to do is to basically convert each clause into a clause that has exactly 3 literals by adding extra variables. And let me just show you what that construction is. So let's say your clause, and I'm just going to use so let's say your clause was x1, single clause. So we are going to convert this, and this is going to be a very simple conversion. So we'll say x1 or u or w, and x1 or u or not w, and x1 or not u or w, and x1 or not u or not W. Right? This is just putting all possible settings of the literals U and V with negation. So no matter what you set U and W to be, you're just going to end up with x1 as one of the clauses, and then that has to be satisfied. So x1 is satisfiable if and only if these four clauses together are satisfiable. If you have x1 or x2, you just add a single dummy variable. So you say x1 or x2 or z, and x1 or x2 or not z. Okay, and in general, if you have x1 or x2 up to some xk, or k could be larger than 3, then what you do is you cascade this argument. You say x1 or x2, or so now I'm just going to call these y1. And so you'll see what I'm going to do over here. And x3 or not of y1 or y2, and x4 or not of y2 or y3, and x5 or not of y3 or y4, so on and so forth. So what this is saying is, if this is satisfiable, then you have to be able to satisfy everything else. You have to be able to satisfy all of these. And so the way the trick works is you can just think of it as I suppose the best way to think of it is really just by applying this idea. You could apply it over and over again. Or another way of looking at this is to say that so if y1 is false, so let's just say you set y1 to be false, then it would make this one true. So you could just set y2 to be false, y3 to be false, and all of those others to be false, and then you have to satisfy x1 or x2. If you set y1 to be true, then you get rid of this clause, but now this still survives. And then if y2 is false, then you have to satisfy x3, so on and so forth. So verify that x1 or x2 up to xk is satisfiable if and only if whatever I wrote here, this is satisfiable. Okay, that's an exercise. And then this basically completes the reduction, because now you can note that the size is obviously it's polynomially sized. So the new formula in this case is actually linear sized, has size O of n, where n was the size of the original formula. Okay, so this is it's a clever construction, it's a relatively simple one. So this shows that 3-sat is NP-complete, and that's because we reduce an NP-complete language to 3-sat. Any questions about this? Any questions? Okay. Any questions? Sure, this is clear. So 3-sat is NP-complete. Now appears probably one of the first what's called a threshold phenomenon that you'll see, that there's a jump in complexity. There's a jump in complexity when you go from 2-sat to 3-sat. 2-sat is actually NP. So 2-sat can be solved in polynomial time. It's not that obvious. It's not that obvious. 3-sat is NP complete. So we don't, if 3-sat could be solved in polynomial time, then all of NP would be solvable in polynomial time. All NP problems. Whereas 2-sat is actually NP. So let me sketch out the basic idea. I may or may not write the proof in gory detail, and I might leave it as an exercise for you to fill in the details. Let me explain the basic idea. So I'll say the proof idea. So let's look at what a 2-sat instance looks like. So you'll say like x5 or x3 bar and x10 or x5 or x3 or x20, so on and so forth. So let's pick a clause. And you could ask, should x5 be 0 or 1? Again, so this is usually my false and this is true. So if you set it to be true, well then of course you know that that becomes true. So you don't have to worry about that. And you don't have to worry about this clause. So you get rid of a bunch of clauses that become true. But suppose you set it to be false. Now what? So suppose x5 you set it to be false. What can you infer from that?
Then x3 is forced to have a particular value.
Then x3 is forced to have a particular value, in this case false. Now x3 is false, so you go there, which forces x20 to become true, which may force something else to become true, so on and so forth. So what happens is every time you make a choice of a variable, now what could happen is if you follow this process, so let's just say we said x3 has to be false, right? So we said if x5 was 0, that implies x3 is 0, which implies x20 is 1, and then maybe somewhere down the line you have x20 0 or x5. But if x5 is 1, that implies that x20 is 1. That would imply that x5 is equal to 1. And now you have a contradiction. So you have this cycle. You start from x5. You set x5 to something. And you keep walking through this process. And you end up setting x5 to its negation. So you know that x5 cannot be 0. Therefore, x5 has to be 1. So in some sense, you can treat each clause as an implication. Either you set that to be, either you get rid of the clause, or you actually discover a setting for another variable. Okay, so does this make sense? And so the way that, let me hint out how you would solve this in linear time. And there are sort of multiple ways of thinking about this. Let me give you an algorithm that is not the most efficient, but on the other hand, I think it adds a lot of clarity to what is happening. So create variables, create a graph G equal to V comma E directed where there are, okay, so let's just start with this clause, and let's say there are n variables and there are m clauses. Okay, so I'm going to create a graph where there are 2n variables, and 2m directed edges. So my variables are going to be of the form, these are basically going to indicate me setting, these are going to indicate that I'm setting a variable to some value. So x, I'll say I is equal to 1, 0, and xi is equal to 1. So I'm going to have these 2n variables here. Now take a clause. So let's say you have a clause xi or xj. I can interpret that as basically saying not of xi implies xj, and not of xj implies xi, right? This is equivalent. These are two equivalent. This is just saying that if you choose the value of xi to be false, then you're forced to set xj to be true. So now I represent this as edges in the graph. So I'll say xj is equal to 1. So if this is 0, then this has to be 1. And xj, if this is 0, then this has to be 1. Right? So I get these implications. Over here. And so I get this entire graph. So this is going to be my graph G. This is G. So what does this mean? If you set xi to be 0, then you have to set xj to 1. But maybe xj has some out neighbors. So you have to set that to be 1. So you can keep following paths. And if the paths ever lead you back to the opposite setting, then you know that that is not feasible. Does this make sense? So if there is a directed path from xi taking a value from this node to xi taking the negation of that, then you know that you cannot set xi to b in any satisfying assignment. Then xi must be equal to not b in any satisfying assignment. So if there is a directed path, then you know that. So if you find a directed path, then what you can do is you can effectively set that variable to be 1 or to whatever it is, and you can shrink your instance. Now once you've set it, you can get rid of a bunch of clauses, follow through all the implications, and then you'll have a smaller sat instance, smaller two-sat instance. So now, once xi is equal to b is sort of set, or I should say once xi is set to the negation of b, where b is either 0 or 1. I should have explained. B is just a bit, 0 or 1. Remove all satisfied clauses. So you remove all the satisfied clauses, and these are the ones satisfied by xi equal to b and its implications. And now you just recursively solve. This leaves, some C prime, which is a 2CNF with fewer clauses. And then you go ahead and try to find an implication here, and you proceed. And if at some point there is no contradiction. So what is a contradiction? That's a path of this form. So I'll call this a contradiction. And this you can find using DFS or BFS or anything. So you can just check this using DFS or BFS. And so if at some point there is no contradiction, then phi is satisfiable. So obviously this is a proof sketch, so I didn't give you all the details, but this is the basic construction. And all constructions are usually just some variant of this, and if you're careful, you can basically just do it in linear time. You just do a collection. You can just do like DFS or BFS, or you find like strongly connected components, and then you can deal with each of them separately. So it's a fairly straightforward algorithm once you get the idea. Once you have this construction, the algorithm is not particularly hard. So what this says is, this is sort of an important dichotomy that we have proven now. We've proven that 3-sat is NP-complete, but 2-sat is actually NP. So this difference from 2 to 3 leads to this huge jump in complexity, which we will see in many different instances this will happen. That changing one innocuous variable suddenly makes an easy problem hard. So I'll end here. In the next lecture, we'll do more NP-completeness reductions.